because these are pretty awesome. I'm very happy with these things. Support vector machines are extremely valuable. Pretty much you just put a straight line through the data. But since you can use modified data, that straight line can be something that looks curved. So here we're going to have a data set, and what we're going to use is just a synthetic group of dots. We're going to practice rather than downloading meaningful images, we're just going to generate some synthetic data so we can make a model and see how well it performs. So I'll go through this Google nonsense again. Of course, they're giving me a lot of service for free, so you know, I can't complain too much about them making me log in over and over.
If anybody's not on the scoreboard and wants to be, just raise your hand and we can help you get on there.
Yeah. All right. So this will create some data. It's just going to create some data that's randomly distributed with centers of the cluster here and a standard deviation there. So you get some red and blue dots in a two-dimensional space after it installs the libraries and such. And now we're using the SecML library, which we're going to use a lot. The SecML is security machine learning library, and it includes attacks and defenses, which we're going to play with. So here's the data, blue dots and red dots, and you're supposed to separate them. And as you can see, there's a complete separation. There's no, you could just draw a line here. Now you could do it a lot of ways. You could draw a horizontal line like this and get 100% success. You could draw an almost vertical line like this and get success. So what line should you choose? And the answer is, in support vector machines, you choose the border that gives you the greatest width of the street, so the most efficient separation. So you figure out what the width is to touch the instance that would make it wrong, and this way, so there's the width of the border here. See, one line has the widest street, and that's what you call the right one in the world of support vector machines. So we can create and train this model. Oops. There we go. All right. And there it is, and here's the master. You see it chose this line as the best one. Now we're going to see what happens when you scale the data. I keep mentioning many times, you don't want your data to be in the wrong scale. So if you multiply the scale by 100 for the vertical axis, all right, and then work with the scaled data, TRX expanded. It's the same data, but this is now going up by hundreds, and this is going up by ones. And now, if you train the model on that, down here, you get a completely different fit because you told it, when you're evaluating the width of the street, this distance is 100 times more important than this distance. That's what you're telling it. It's using these numbers, so it's not willing to make vertical errors at all. Instead of this fit up here, where it was happy to be that far from that dot, it now is very unhappy to be that far from that dot. It wants to be way down here. So that's the problem with scaling, and that's going to appear over and over again as we go ahead. That's why you have to massage your data. Now, if you make your data set overlap, by having larger standard deviation, then you now have to add a regularization parameter. Now you're going to have to allow soft scalar, not soft borders, where it's allowed to have some degree of error. And you add, this is a smoothing parameter. You have to do this almost all the time. Remember way back in the first one, where you had a funny curve, we had 4,000 parameters to fit a curve that went up and down like 3 or 4 times. Clearly, you could that's way too many parameters. There'd be many possible solutions. So in order to avoid having crazy solutions, you smoothed out the answer with a regularization parameter. And here, it's this parameter called C. So you add this parameter C, which prevents it from having smoothed it out. If you smooth it out too much, it has a terrible fit where it calls everything blue, which means all the red ones are wrong. But then you hit a reasonable region of C where it has a reasonable solution, and that's the game, and you can play with it. This is going to be a problem, and again, this is what humans have to feed in. They call them hyperparameters. You have the data, and you have your model trying to fit the data, and then you add extra parameters to just make the model not just fit a border, but fit a smooth border, to try to tell it how to ignore the noise. And therefore it will be a larger error, but presumably more representative of the actual data underneath. But now, if you try to use a curved data set that you can't separate with a line, then you've got a different situation, and they have a library to make these so-called moons data sets for this reason. So here we got blue ones and green ones, and we're trying to tell them apart, but they're curved, so we can't do it with just a line. So you can make a model here, and it will show you the structure of your model. All right, it's going to have, now it's going to make polynomial features. What it does is it will now, in addition to having just x and y, it will make x squared and x cubed and x2 squared and x2 cubed and put it in a multi-dimensional space. Because if you make new synthetic parameters out of the existing ones, now in this high-dimensional space, a straight line will now make the border. And like I said, this is like putting your data on log paper or something. You find different combinations of the data to use to fit, so that now it can still fit it with a straight line in a strange space working on combinations of the input parameters, synthetic features, polynomial features. So now I can fit, say, cubic polynomials. Ax cubed plus bx squared plus cx plus d is a straight line if you have an axis for x and x squared and x cubed. It's a hyperplane in a high-dimensional space. That's why straight lines, this is a straight line. It just doesn't look like it in this projection. That's a straight line in the space that includes x1 and x1 squared and x1 cubed, and x2 and x2 squared and x2 cubed. That's the beauty of it. So straight lines can be far more powerful than you might think. And those are support vector machines. And by the way, I forgot to mention why they call them support vectors, which is unbelievable. If you do the hard decision version of this, consider this line. What determined this line? The only thing that determines this line, let me get back to this one there, is these two dots. All the rest of the dots contribute nothing. These are called the support vectors. Those two dots determine the fit. All the rest don't affect it at all, which is really strange. But that's the way support vector machines work. Of course, when you have a soft boundary, then you include some of the ones around here and weight them, instead of just basing it on the ones right near the edge. But the original support vector machine depends only on the dots right on the edge of the street, which is screwy, but it makes them fast. And so you can have various flags defined with them. Those are support vector machines, and then I remember we talked about this. Let me bring back that presentation we looked at the start to point out where we are. It should be my recent one, and so it is. There's a figure here. Wait, that's not right. Let me try to get the right one here. This one here. File, open recent. All right. Oh, that's pages. That's why I got to have the PowerPoint. Fine. It's display or something. I'm going to do it this way. I can't remember the names of things. Lec. There it is. This is what I want. Keynote. That's the name of it. All right. There's a diagram here I said was kind of an overview of everything we're going to do, or almost everything. There, this is it. These are the types of machine learning models. So what we just did was support vector machines, which are surprisingly powerful. And down here, we're going to try some of these others as we go ahead. All of these are in here. The different kinds of neural nets, the different kinds of machine learning. Not all of them are neural nets. All right, so let me stop.